All right, let's look at Theorem 1, Existence and the Uniqueness of Isometries. All right, let's say you have a triangle ABC which is congruent to triangle XYZ. All right, then there exists a unique isometry F such that f of A equals X, f of B equals Y, and f of C equals Z. Right? So there are two components. First component is the proof of existence. All right, so this existence is demonstrated in the Theorem 2 demo, so I'm going to skip that. But let's focus on proof of uniqueness, right? So how come they cannot be two distinct isometries having having this property? Right? So as usual, let's assume that they're two distinct isometries and then try to get in trouble. So here we're going to assume that there exists two distinct isometry let's call it F and G or something like that, such that, right, so they're going to give you F of A is exactly the same as G of A, which is X, and F of B is exactly the same as G of B, which is equal to Y. And then you have a F of C is equal to F of C, G of C, which is equal to Z. All right, so what's wrong with that? All right, then you can see that if you apply G inverse, right, it's an isometry, so it's a transformation, so inverse exists. If you apply G inverse to all of these guys, we're going to get this. So G inverse of F of A is obviously equal to A. Right? G inverse of F of B is equal to B. And the G inverse of F of C is obviously equal to C. Right, so by lemma, we have three non-collinear fixed points. So we know that so this is by lemma. We know that G inverse of F is an identity map, right? Then we can apply G to both sides. We know that the F is equal to G, right? Which is a contradiction because we said that these are distinct. So we know that this is a contradiction. Right, so therefore, there could be only one isometry with that condition, right? Mapping A to X, B to Y, and C to Z. Right, so that's it. I hope that this was clear.